Welcome to Sleep Plus Knowledge. I'm glad you found your way here tonight. Maybe the day has been long, or perhaps you simply find comfort in learning about the quiet wonders beyond our world. Whatever brings you here, this is your time to let go, to breathe deeply, and to let your thoughts drift like clouds across an evening sky. Tonight, we'll journey through space and time together, exploring the gentle mysteries of our cosmos. We'll visit distant worlds, learn about the forces that shape reality, and discover facts that might surprise you or simply fade into the comfortable rhythm of approaching sleep. If you find peace in these words and wish to help others discover this calm place, feel free to like and subscribe. But for now, there's nothing to do except rest. So settle in, close your eyes if you'd like, and let's begin our quiet exploration of the universe. The sun loses millions of tons of mass every single second. Our star, the sun, is constantly transforming itself. Deep in its core, hydrogen atoms fuse into helium, releasing the energy that lights our world. But this process comes with a cost. Every second, the sun converts about 4 million tons of mass directly into pure energy through Einstein's famous equation. That mass doesn't disappear. It becomes the light and heat that reaches Earth. At the same time, the solar wind carries away more material, streams of charged particles flowing outward into space. It sounds dramatic, but the sun is so massive that even after billions of years of this constant loss, it has barely changed. It will continue shining steadily for billions more years, gently burning, slowly fading, a patient beacon in our corner of the galaxy. There are moons in our solar system with subsurface oceans. Beneath the frozen surfaces of several distant moons, vast oceans may be quietly flowing. Europa, the moon of Jupiter, covered in ice, but tidal forces from Jupiter's gravity heat its interior, possibly maintaining a liquid water ocean beneath the crust. Saturn's moon Enceladus also shows signs of such an ocean, with geysers of water vapor erupting from cracks in its icy shell. Even Titan, Saturn's largest moon, may harbor a liquid water ocean deep below its surface of frozen methane and ethane. These hidden seas could be warm, dark, and rich in chemistry. They represent some of the most intriguing places in our solar system to search for life. Quiet worlds within worlds, sealed beneath ice and waiting. Light takes 8 minutes to travel from the sun to Earth. When you see sunlight streaming through a window or feel its warmth on your skin, you're experiencing something that left the sun more than 8 minutes ago. Light travels at about 300,000 kilometers per second, fastest speed possible in our universe. Yet even at that incredible velocity, it still takes time to cross the 150 million kilometers between the sun and Earth. This means we never see the sun as it is right now, only as it was 8 minutes in the past. If the sun suddenly vanished, we wouldn't know for 8 minutes. The light, the warmth, everything would continue normally for that brief span. Then darkness would come. Not instantly, but after those 8 minutes had passed. It's a gentle reminder that even light has a journey. Saturn's rings are surprisingly young. The magnificent rings of Saturn, those gleaming bands that make it perhaps the most beautiful planet in our solar system, may be younger than the dinosaurs. For decades, scientists assumed the rings were ancient, formed when the solar system itself was born. But recent data from the Cassini spacecraft suggests they may be only 10 to 100 million years old. That's recent in cosmic terms. The rings are made of billions of chunks of ice, some as small as grains of sand, others as large as mountains. They may have formed when a comet or moon wandered too close to Saturn and was torn apart by gravity. These particles now orbit in thin, flat sheets, reflecting sunlight with a brilliance that reaches across the solar system. And someday, perhaps in another 100 million years, they may be gone, scattered, or absorbed. For now, they shine. Mars has the largest volcano in the solar system. On Mars, rising from the rusty plains, stands Olympus Mons, a volcanic mountain so vast it defies easy comprehension. It's nearly 3 times the height of Mount Everest and so wide that if you stood on its summit, you couldn't see the base. The horizon would curve away before your eyes could reach it. This giant volcano is a shield volcano, built layer by layer from countless eruptions of flowing lava over millions of years. Mars has lower gravity than Earth, which allowed the volcano to grow higher without collapsing under its own weight. Olympus Mons is likely extinct now, cold and silent, its last eruptions perhaps millions of years ago, but it remains a monument to the violent, creative forces that shaped the early solar system, a sleeping giant on a sleeping world. The moon is gradually slowing Earth's rotation. Every year, Earth's day gets a tiny bit longer, just a few milliseconds. The cause is the moon. As it orbits our planet, the moon's gravity pulls on Earth's oceans, creating tides. These tides create friction, a subtle drag that gradually slows Earth's rotation. At the same time, this interaction pushes the moon farther away, about 3.8 centimeters per year. Billions of years ago, Earth's day was much shorter, perhaps only 5 or 6 hours long, and the moon loomed much larger in the sky. In the distant future, if nothing else intervenes, Earth and the moon may become tidally locked, always showing the same face to each other, like two dancers frozen in an eternal embrace. For now, they continue their slow gravitational dance, invisible but constant. Jupiter protects Earth from asteroids. Jupiter, the largest planet in our solar system, acts as a cosmic guardian for the inner planets. Its immense gravity influences the orbits of countless asteroids and comets in the outer solar system. Many objects that might otherwise fall toward Earth are instead captured by Jupiter's pull, drawn into collision with the giant planet, or flung out of the solar system entirely. This isn't perfect protection. Some objects still get through, but simulations suggest that without Jupiter, Earth would be struck by asteroids far more frequently, perhaps making complex life much harder to develop. In a sense, we owe our existence partly to Jupiter's presence, a massive, patient sentinel keeping watch at the edge of the inner solar system. Neptune has winds faster than the speed of sound. Neptune, the most distant planet from the Sun, is a world of deep blue clouds and violent weather. Despite being so far from the Sun's warmth, Neptune generates powerful storms with winds that can reach speeds of over 2,000 kilometers per hour. That's faster than the speed of sound. These supersonic winds race around the planet in jet streams, driven by heat from Neptune's interior. The planet radiates more energy than it receives from the Sun, meaning something deep inside is still generating warmth, perhaps leftover heat from its formation billions of years ago. One storm, observed in 1989, was dubbed the Great Dark Spot, a massive hurricane-like system larger than Earth. It has since disappeared, replaced by other storms. Neptune is a world of constant motion, churning and howling in the outer darkness. Venus has a day longer than its year. Venus is the second planet from the Sun, roughly Earth's size, but radically different in almost every other way. One of its strangest features is its rotation. Venus spins so slowly that a single day, one full rotation on its axis, takes longer than its year, the time it takes to orbit the Sunday. A day on Venus lasts about 243 Earth days, while its year is only 225 Earth days. To make things even stranger, Venus rotates backward compared to most other planets. If you could stand on Venus, the sun would rise in the west and set in the east. The reasons for this slow, backward spin aren't entirely clear. Perhaps a massive collision early in its history knocked it into this unusual rotation. Whatever the cause, Venus drifts through space at its own slow, deliberate pace. The Great Red Spot on Jupiter is shrinking. For centuries, astronomers have observed the Great Red Spot, a gigantic storm on Jupiter, larger than Earth itself. This storm has raged for at least 400 years, a swirling oval of red and orange clouds driven by powerful winds. But in recent decades, observers have noticed something unusual. The storm is shrinking. In the 1800s, it was wide enough to fit 3 Earths side by side. Now, it's barely large enough for one. The reasons aren't fully understood. Perhaps changes in Jupiter's atmosphere are draining energy from the storm, or maybe this is just part of a natural cycle. Some scientists wonder if the Great Red Spot will eventually disappear altogether. For now, it continues to spin, a little smaller each year, a fading reminder of Jupiter's ancient fury. Mercury has ice despite being the closest planet to the Sunday Mercury. Scorched by the sun's heat, seems like the last place you'd find ice. During the day, surface temperatures can soar to 430 degrees Celsius. Mercury has no atmosphere to hold heat, and at night, temperatures plunge to minus 180 degrees Celsius. Even stranger, there are craters near Mercury's poles where sunlight never reaches. These permanently shadowed regions are so cold that water ice can survive there, hidden in darkness even on the hottest planet. Radar observations and spacecraft data have confirmed deposits of ice mixed with dust, perhaps delivered by ancient comets. It's a reminder that even in the most extreme places, the universe can hold surprises. Ice on Mercury, shadow on the sun's doorstep. Uranus rotates on its side. Most planets spin upright, with their axes roughly perpendicular to their orbits. But Uranus is tilted over so far that it essentially rolls around the sun like a ball. Its axis is tilted 98 degrees, meaning its poles lie where most planets have their equators. This extreme tilt gives Uranus bizarre seasons. Each pole experiences 42 years of continuous sunlight, followed by 42 years of darkness. The cause of this tilt is unknown, but most scientists believe Uranus was knocked over by a massive collision early in the solar system's history, perhaps with an Earth-sized object. Whatever struck Uranus left it spinning awkwardly, a planet that never quite recovered from an ancient cosmic accident. Pluto has a heart-shaped glacier of frozen nitrogen. When the New Horizons spacecraft flew past Pluto in 2015, it revealed a world far more dynamic and beautiful than anyone expected. One of the most striking features is a bright, heart-shaped region called Tombaugh Regio. Part of this heart is covered by a vast glacier made of frozen nitrogen, carbon monoxide, and methane. These ices flow slowly across Pluto's surface, driven by subtle temperature differences and Pluto's weak gravity. The nitrogen ice is continuously replenished and recycled, making this one of the most geologically active areas on the distant dwarf planet. Pluto, cold and distant, orbiting in near darkness, still has a beating heart of ice. It's a small, quiet world, but not a dead one. Comets have two tails pointing in different directions. When a comet approaches the sun, heat causes its ice to vaporize, forming a glowing cloud called a coma, and two distinct tails. One tail is made of dust, tiny particles released as the ice evaporates. This dust tail is pushed back by the pressure of sunlight and curves gently, following the comet's orbital path. The other tail is made of ionized gas, charged particles that are blown directly away from the sun by the solar wind. This ion tail always points straight away from the sun, forming a narrow, bluish stream. A comet doesn't have a front and a back like a rocket. It simply glows and streams, sculpted by light and wind into a shape that depends entirely on where it is in its journey. Two tails, two forces, one frozen traveler. Asteroids have their own tiny moons. Asteroids aren't just solitary rocks drifting through space. Some have companions, small moons orbiting around them. These moons likely formed when a collision broke off a chunk of the asteroid, or when two asteroids performed a slow gravitational dance and became locked together. The asteroid Ida, for example, has a small moon named Dactyl. Others have two moons, or even systems of several objects orbiting one another. These miniature systems are delicate and strange, held together by gravity so weak you could escape it with a gentle jump. Yet they endure, spinning quietly in the asteroid belt. Tiny worlds, with even tinier worlds in tow. The solar wind creates auroras on other planets. Earth's auroras, the northern and southern lights, are well-known shimmering curtains of green, red, and violet dancing across polar skies. They're caused by charged particles from the sun colliding with Earth's magnetic field and atmosphere. But Earth isn't the only planet with auroras. Jupiter, Saturn, Uranus, and Neptune all have them, sometimes even more spectacular than ours. Jupiter's auroras are powered by volcanic particles from its moon Io, as well as by the solar wind. Saturn's auroras pulse and shimmer across its poles, glowing in ultraviolet light. Even Mars, which has only a weak magnetic field, shows faint auroral glows in certain regions. These lights are a universal phenomenon, a reminder that wherever there is atmosphere, magnetism, and energy, the cosmos finds a way to glow. The asteroid belt isn't crowded like movies suggest. In films, asteroid belts are depicted as dense fields of tumbling rocks, requiring skillful piloting to avoid collisions. In reality, the asteroid belt between Mars and Jupiter is mostly empty space. The asteroids are spread so thinly that if you were standing on one, you likely wouldn't be able to see another with the naked eye. Spacecraft routinely pass through the belt without any risk of collision. The total mass of all asteroids combined is less than that of Earth's moon. The belt isn't a wall or a hazard, just a sparse collection of ancient rubble left over from the solar system's formation, drifting quietly in wide, lonely orbits. Titan is the only moon with a thick atmosphere. Saturn's largest moon, Titan, is unique in the solar system. It's the only moon with a dense atmosphere, thicker even than Earth's. This atmosphere is mostly nitrogen, with traces of methane and other hydrocarbons. The surface pressure is about 50% higher than at sea level on Earth. Titan's atmosphere is so thick and hazy that for a long time we couldn't see through it to the surface below. When the Cassini spacecraft sent the Huygens probe down to Titan's surface in 2005, it revealed a strange, alien landscape. Rivers and lakes of liquid methane and ethane, dunes of dark hydrocarbon sand, and a sky filled with orange smog. Titan is cold, far colder than anywhere on Earth, but it has weather, seasons, and a hydrological cycle, just with methane instead of water. There are Trojan asteroids that share Earth's orbit. Most people know about the asteroid belt, but there are asteroids in other places too. Some share the orbits of planets trapped in gravitational sweet spots called Lagrange points. These are locations where the gravity of the planet and the sun balance perfectly, creating stable regions where objects can remain. Jupiter has thousands of these so-called Trojan asteroids. And in 2010, astronomers discovered that Earth has at least one as well. This asteroid, named 2010 TK7, orbits the Sun in sync with Earth, always staying roughly the same distance away. It's not a threat, just a small companion, a cosmic fellow traveler sharing our path around the Sunday. Io is the most volcanically active body in the solar system. Jupiter's moon Io is a world in turmoil. Its surface is constantly reshaped by volcanic eruptions, with lava flows and plumes of sulfur compounds shooting hundreds of kilometers into space. Io has more than 400 active volcanoes, more than any other object in the solar system. The cause is tidal heating. Io orbits close to Jupiter, and the immense gravity of the giant planet, along with gravitational tugs from neighboring moons, flexes and stretches Io's interior. This constant squeezing generates heat, melting rock, and driving continuous eruptions. Io's surface is a patchwork of yellows, reds, and blacks, sulfur and silicate deposits layered over each other. No ice, no water, just heat and fire. A tortured moon locked in an endless volcanic dance. The sun's core is unimaginably hot and dense. At the very center of the sun, conditions are extreme beyond everyday comprehension. The temperature there is about 15 million degrees Celsius, hot enough to strip electrons from atoms and fuse hydrogen nuclei into helium. The pressure is equally staggering, more than 250 billion times the atmospheric pressure at Earth's surface. In this environment, matter behaves in ways it never could anywhere on Earth. The core is so dense that a single cubic centimeter weighs over 150 grams, denser than lead. Yet this core occupies only a tiny fraction of the sun's volume. All the light and heat we receive comes from energy generated in this small, fiercely burning heart. It takes tens of thousands of years for that energy to work its way to the surface and finally escape into space. Enceladus has geysers that spray water into space. Saturn's small moon, Enceladus, is covered in bright, clean ice, reflecting sunlight with remarkable brilliance. But it's not a dead, frozen world. Near its south pole, enormous geysers erupt from deep cracks in the ice, shooting jets of water vapor, ice crystals, and organic molecules hundreds of kilometers into space. Some of this material falls back to the surface as snow. The rest escapes into orbit around Saturn, helping to form one of the planet's faint rings. These geysers suggest that beneath Enceladus's icy crust lies a liquid ocean, kept warm by tidal heating from Saturn's gravity. That hidden ocean may contain the ingredients for life. Enceladus, small and quiet, may hold one of the solar system's greatest secrets. Venus's atmosphere is thick enough to crush spacecraft. Venus is often called Earth's twin because it's similar in size and composition, but its atmosphere is nothing like ours. The surface pressure on Venus is about 90 times greater than Earth's, equivalent to being a kilometer underwater in Earth's oceans. The atmosphere is almost entirely carbon dioxide, creating a runaway greenhouse effect that heats the surface to around 465 degrees Celsius, hot enough to melt lead. The thick atmosphere also creates crushing pressure that has destroyed every lander sent to Venus within hours. Soviet Venera probes in the 1,970 seconds and 80 seconds managed to send back a few images before succumbing to the heat and pressure. Venus is beautiful from orbit, shrouded in white clouds, but its surface is one of the most hostile environments in the solar system. Mars once had rivers, lakes, and possibly an ocean. Today, Mars is a dry, dusty desert, but billions of years ago, it was a very different world. Ancient riverbeds, lake basins, and mineral deposits show that liquid water once flowed on the surface. Some scientists believe Mars may have had an ocean covering much of its northern hemisphere. The climate was warmer and wetter, with a thicker atmosphere that could hold heat and support liquid water. But over time, Mars lost most of its atmosphere. Without a strong magnetic field to protect it, the solar wind gradually stripped away the air. As the atmosphere thinned, the water evaporated or froze, and Mars became the cold, barren world we see today. But beneath the surface, ice remains, and perhaps somewhere, liquid water still flows in hidden aquifers. The solar system is moving through the galaxy at incredible speed. It's easy to think of the sun as fixed in space, with planets orbiting around it. But the sun itself is in motion, orbiting the center of the Milky Way galaxy. It travels at about 828,000 kilometers per hour, taking roughly 230 million years to complete one orbit. This means that since the time of the dinosaurs, the solar system has moved less than halfway around the galaxy. As it moves, the sun bobs up and down through the galactic plane, like a horse on a cosmic carousel. We're also moving toward a point in the sky called the solar apex, near the constellation Hercules. All this motion is smooth and steady, imperceptible in daily life, but real. We are passengers on a star sailing through the galaxy. Europa's ice crust may be dozens of kilometers thick. Jupiter's moon Europa is covered in a shell of water ice, smooth and crisscrossed with long, dark cracks. Beneath this ice, scientists believe, lies a global ocean of liquid water, kept from freezing by tidal heating from Jupiter's gravity. But how thick is the ice? Estimates range from a few kilometers to several dozen kilometers. If the ice is thin, it might be possible for future missions to drill through and explore the ocean below. If it's thick, reaching the water will be much harder. The surface itself is constantly renewed by geological activity, with ice shifting, cracking, and refreezing, erasing craters and smoothing the terrain. Europa's icy shell is both a barrier and a window, hiding an ocean that might harbor life. Jupiter radiates more heat than it receives from the Sunday. Jupiter is so far from the Sun that it receives only a fraction of the sunlight that Earth does. Yet when scientists measure the heat coming from Jupiter, they find something surprising. The planet emits about twice as much energy as it absorbs from the Sunday. This extra heat comes from within. Jupiter is still slowly contracting under its own gravity, a process that began when it formed 4.6 billion years ago. As it contracts, gravitational potential energy is converted into heat, warming the planet from the inside. This internal heat drives Jupiter's weather, including its powerful storms and jet streams. In a sense, Jupiter is still glowing faintly with the memory of its birth. Saturn's moon Mimas looks like the Death Star. Mimas is a small, icy moon of Saturn, heavily cratered and unremarkable in most ways, except for one feature, Herschel crater. This enormous impact crater is about 1/3 the diameter of Mimas itself, with the central peak rising from the crater floor. From certain angles, Mimas looks almost exactly like the Death Star from Star Wars, complete with a prominent circular dish. The resemblance is purely coincidental. The crater formed from a collision that nearly destroyed Mimas. Had the impact been any stronger, the moon might have shattered completely. Instead, it survived, scarred but intact, forever bearing the mark of an ancient cosmic violence. There are more stars in the universe than grains of sand on Earth. When people try to convey the vastness of the universe, they often use this comparison, and it's true. The number of stars in the observable universe is estimated at around 10 to the power of 24, or a trillion. That's more than all the grains of sand on all the beaches and deserts on Earth. Each of those stars is a sun, some smaller than ours, some vastly larger. Many have planets. Some of those planets may have moons. The numbers become almost meaningless, too large to hold in the mind. But the feeling remains. The universe is unimaginably vast, filled with more light, more worlds, and more possibilities than we can ever fully comprehend. Our solar system has a tail. The solar system doesn't just sit still in space. As it moves through the galaxy, the sun's magnetic field and the solar wind create a protective bubble called the heliosphere. This bubble shields the planets from interstellar radiation and cosmic rays. But like a comet, the heliosphere has a tail. As the solar system moves through the thin gas between stars, the heliosphere is compressed in front and stretched out behind, forming a long tail called the heliotail. This tail extends for billions of kilometers, trailing behind us as we move through the galaxy. It's invisible, but spacecraft like Voyager have helped map its shape. We are not just orbiting the Sunday. We're all traveling together through space, leaving a wake in the interstellar medium. The coldest place in the solar system is on the Moon. You might expect the coldest place to be on Pluto or in the shadowed depths of space, but surprisingly, some of the coldest temperatures measured in the solar system were found in permanently shadowed craters near the Moon's south pole. These craters never receive sunlight. With no atmosphere to distribute heat, temperatures there drop to about minus 240 degrees Celsius, colder than the surface of Pluto. These frigid regions may contain water, ice, reserved in the darkness for billions of years. They're called cold traps, and they're of great interest for future lunar exploration. In the shadowed corners of our nearest neighbor, hidden cold endures. Mars has the longest canyon in the solar system. Valles Marineris is a system of canyons on Mars that dwarfs anything on Earth. It stretches over 4,000 kilometers long, up to 600 kilometers wide, and reaches depths of 7 kilometers. If it were on Earth, it would stretch from New York to Los Angeles. By comparison, the Grand Canyon is only about 450 kilometers long and 1.8 kilometers deep. Valles Marineris wasn't carved by water. Instead, it likely formed billions of years ago when the Martian crust split and collapsed, perhaps due to volcanic activity or tectonic stress. Over time, landslides, wind, and perhaps ancient floods shaped its walls. Walking through this canyon would take months, surrounded by towering cliffs of layered rock. The scar across an entire planet. Neptune was discovered through mathematics before it was seen. In the early 1800s, astronomers studying Uranus noticed something odd. Its orbit wasn't quite following the predictions of Newton's laws. Something was pulling on it, perturbing its path. Two mathematicians, Urbain Le Verrier in France and John Couch Adams in England, independently calculated where an unknown planet must be located to explain these irregularities. In 1846, using Le Verrier's predictions, astronomers pointed their telescopes to the predicted spot and found Neptune, almost exactly where the math said it would be. It was a triumph of science, a planet discovered not by looking, but by thinking. Neptune was seen because someone believed the numbers. Callisto is one of the most heavily cratered objects in the solar system. Jupiter's moon Callisto is ancient and battered. Its surface is covered with impact craters, layered over each other from billions of years of collisions. Unlike some other moons that have been resurfaced by volcanic or geological activity, Callisto's surface is largely unchanged since the early solar system. It's a frozen record of cosmic violence, a testament to the chaotic era when the solar system was still forming. The lack of geological activity suggests that Callisto's interior is cold and inactive. It may have a subsurface ocean, but if so, it lies deep beneath an icy, cratered shell. Callisto is a quiet, ancient witness, pockmarked and still. The sun's atmosphere is hotter than its surface. The surface of the sun, the photosphere, has a temperature of about 5,500 degrees Celsius. But as you move outward into the sun's atmosphere, something strange happens. The temperature rises. The outermost layer, the corona, reaches temperatures of several million degrees. This seems to violate common sense. How can the atmosphere be hotter than the surface below it? Scientists believe the answer involves magnetic fields. The sun's magnetic field lines twist, snap, and release energy in the corona, heating the gas to extreme temperatures. This process is still not fully understood, but it's one of the great puzzles of solar physics. The sun's crown burns hotter than its face. There are more than 200 moons in our solar system. When we think of the solar system, we often focus on the planets, but they're accompanied by a host of moons, more than 200 confirmed so far, with more being discovered regularly. Some, like Earth's moon or Jupiter's Ganymede, are large and geologically interesting. Others are tiny, irregularly shaped chunks of rock or ice captured from the asteroid belt. Saturn alone has over 80 known moons, ranging from massive Titan to tiny moonlets embedded in its rings. Each moon is unique, shaped by different forces and histories. Together, they form a diverse family of worlds, orbiting in the shadows of giants. The Earth's core is as hot as the surface of the sunday. Deep beneath your feet, at the center of the Earth, lies the inner core, a solid sphere of iron and nickel about 1,200 kilometers in diameter. The temperature there is estimated at around 5,200 degrees Celsius, roughly the same as the sun's surface. This heat comes from leftover energy from Earth's formation and from radioactive decay of elements deep in the mantle. The inner core is solid despite the heat because the pressure is so immense, over 3 million times atmospheric pressure, that the iron cannot melt. Surrounding the inner core is the liquid outer core, where swirling currents of molten metal generate Earth's magnetic field. Our planet has a hidden furnace, burning silently at its heart. Jupiter's Great Red Spot could swallow Earth whole. The Great Red Spot is a storm on Jupiter, an anticyclonic vortex that has been raging for centuries. At its largest, it was over 40,000 kilometers wide, large enough to fit 2 or 3 Earths side by side. Even as it shrinks, it remains bigger than our entire planet. Winds at the edge of the storm reach speeds of up to 450 kilometers per hour. The storm's red color comes from complex chemicals in Jupiter's atmosphere, though scientists aren't entirely sure which compounds are responsible. Inside the Great Red Spot, the atmosphere churns and swirls in patterns that change over days and weeks, a constantly evolving maelstrom that dwarfs the largest hurricanes Earth has ever seen. Ganymede is the largest moon in the solar system. Ganymede, one of Jupiter's moons, holds the title of the largest moon in the solar system. It's even bigger than the planet Mercury, with a diameter of 5,268 kilometers. Ganymede is the only moon known to have its own magnetic field, generated by a liquid iron core deep inside. Its surface is a mix of ancient, heavily cratered dark regions and younger grooved terrain that has been reshaped by tectonic activity. Beneath the surface, Ganymede is thought to have a subsurface ocean, sandwiched between layers of ice. Despite its size, Ganymede is still just a moon, bound to Jupiter, locked in a gravitational embrace with one of the solar system's giants. The Sun contains 99.8% of the solar system's mass. When we think about the solar system, we imagine planets, moons, asteroids, and comets. But almost all of the mass is in the Sunday Jupiter, the largest planet. It contains most of what's left. All the other planets, moons, and debris combined make up less than 0.2% of the total mass. The Sun is the anchor, the center of gravity around which everything else revolves. Its immense mass creates the gravitational pull that keeps the planets in their orbits. Without the Sun, there would be no solar system, just a scattered collection of objects drifting through space. The sun is not just the brightest object in our sky. It is, in almost every sense, the solar system itself. Mars's sky is butterscotch colored during the day. On Earth, we're used to a blue sky, but on Mars, the sky is a different color entirely. During the day, it appears yellowish-brown or butterscotch, a result of fine dust particles suspended in the thin atmosphere. These particles scatter sunlight in a way that gives the Martian sky its distinctive hue. At sunset, however, the colors reverse. While Earth's sunsets are red and orange, Martian sunsets are blue. The dust scatters red light, but the sun's direct rays appear bluish as they pass through the dusty atmosphere. Standing on Mars, you'd see an alien sky, familiar yet wrong. A world painted in unexpected colors. There may be a ninth planet far beyond Neptune. In the outer reaches of the solar system, beyond Neptune and Pluto, something strange is happening. Several distant objects in the Kuiper Belt have orbits that seem to be aligned in unusual ways, as if they're being influenced by the gravity of something large and unseen. Some astronomers believe this could be evidence of a ninth planet, a world several times the mass of Earth, orbiting the Sun at a great distance. This hypothetical planet, often called Planet 9, has never been directly observed. It's too far away and too faint. The math suggests it might be there, a hidden giant lurking in the darkness. The search continues, telescopes scanning the sky for a world that may or may not exist. The sunsets on Uranus last for over 40 years. Uranus is tilted so far on its axis that its poles point almost directly at the sun during certain parts of its orbit. This creates the most extreme seasons in the solar system. Each pole experiences 42 years of continuous sunlight, followed by 42 years of continuous darkness. Imagine a sunset that lasts for decades. The sun slowly circling the horizon, dipping lower and lower over years until it finally disappears. Then, 42 years of night. No sunrise, no blue sky, just darkness and stars. Eventually, the sun returns, creeping back above the horizon for another 42-year day. It's a slow, patient rhythm, played out over a human lifetime. A world where seasons are measured in generations. The solar system orbits the center of the Milky Way. Everything in the galaxy, including our solar system, orbits the galactic center, a region containing a supermassive black hole called Sagittarius A Astris. This black hole has a mass of about 4 million times that of the Sun Day. The solar system is located about 26,000 light years from the galactic center in one of the Milky Way's spiral arms. At our current speed, it takes about 230 million years to complete one full orbit. Dinosaurs roamed the Earth the last time we were in this part of the galaxy. The motion is smooth and imperceptible, but it's real. We are all orbiting the center of the galaxy together, carried by gravity on a journey that spans hundreds of millions of years. Phobos is slowly falling toward Mars. Mars has two small moons, Phobos and Deimos. Both are thought to be captured asteroids, dark and irregularly shaped. But Phobos has an unusual fate. It orbits Mars very closely, just 6,000 kilometers above the surface, closer than any other moon in the solar system orbits its planet. Tidal forces between Mars and Phobos are gradually slowing Phobos' orbit, causing it to spiral inward. In about 50 million years, it will either collide with Mars or break apart under tidal stress, forming a ring around the planet. For now, Phobos races around Mars 3 times a day, a small, doomed moon, slowly falling. The asteroid belt formed because Jupiter prevented a planet from forming there. Between Mars and Jupiter lies the asteroid belt, a region filled with rocky debris. You might expect this material to have coalesced into a planet, but it never did. Jupiter's immense gravity stirred up the region, decreasing the velocities of objects and preventing them from sticking together. Instead of building a planet, collisions broke rocks apart rather than merging them. Over time, the asteroid belt settled into its current state, a collection of leftover building material, frozen in place by Jupiter's gravitational influence. If Jupiter hadn't formed, there might be another rocky planet in that orbit. Instead, there's only rubble and silence. The Sun will eventually expand and swallow the inner planets. The Sun is currently in the middle of its life, a stable yellow star fusing hydrogen into helium. But in about 5 billion years, it will run out of hydrogen fuel in its core. When that happens, the core will contract and heat up, while the outer layers expand dramatically. The Sun will become a red giant, swelling to perhaps 100 times its current size. At that point, it will likely engulf Mercury and Venus. Earth may survive, but just barely. Orbiting at the very edge of the Sun's expanded atmosphere, the oceans will have boiled away long before then. Life, if any remains, will have fled or perished. Eventually, the Sun will shed its outer layers, leaving behind a white dwarf, a cooling ember of its former self. Miranda has some of the most extreme terrain in the solar system. Miranda, the smallest of Uranus's 5 major moons, is one of the strangest objects we've seen. Its surface is a chaotic mix of terrains. Ancient cratered plains next to massive cliffs and grooved regions that look like they've been torn apart and reassembled. One cliff, Verona Rupes, is nearly 20 kilometers high, the tallest known cliff in the solar system. If you fell from the top in Miranda's weak gravity, it would take about 12 minutes to reach the bottom. Scientists aren't sure what caused Miranda's bizarre landscape. It may have been shattered by a massive impact and reassembled by gravity, or internal heat may have reshaped its surface. Either way, Miranda is a broken, haunting world. The Kuiper Belt extends far beyond Pluto. Pluto is often thought of as the edge of the solar system, but it's really just the beginning of a much larger region called the Kuiper Belt. This belt extends from about 30 astronomical units, Neptune's orbit, out to roughly 50 AU, filled with icy bodies left over from the solar system's formation. These objects are mostly small, though some, like Pluto, are large enough to be considered dwarf planets. The Kuiper Belt is a cold, dark frontier, a reminder that the solar system doesn't end with the planets. It fades gradually into the vastness of interstellar space, with scattered, frozen worlds marking the way. You could fit all the planets between Earth and the Moon. It sounds impossible, but it's true. The average distance between Earth and the Moon is about 384,400 kilometers. If you lined up all the planets in the solar system, from Mercury to Neptune, their combined diameters would total roughly 380,000 kilometers. There would even be a little space left over. Of course, this is just a thought experiment. The planets would never actually align this way, and their gravity would tear each other apart. But it's a useful reminder of just how much empty space there is in the solar system. The distances are vast, and the objects, even the planets, are tiny in comparison. Saturn's rings are made of countless individual particles. From a distance, Saturn's rings look solid and smooth, like a flat disk surrounding the planet. But up close, they're revealed to be made of billions of individual particles, each one orbiting Saturn independently. These particles range in size from tiny grains of dust to house-sized chunks of ice. They orbit in thin, flat sheets, held in place by Saturn's gravity and shaped by the gravitational influence of Saturn's moons. Some regions of the rings are dense and bright, others are sparse and dim. The rings are incredibly thin, less than a kilometer thick in most places, yet they span hundreds of thousands of kilometers. They're a dynamic, ever-changing structure, beautiful and delicate. There's lightning on Jupiter, Saturn, and Venus. Lightning isn't unique to Earth. Other planets with atmospheres also experience electrical storms. Jupiter's lightning is extremely powerful, with bolts up to 3 times more energetic than the largest storms on Earth. They occur deep in Jupiter's atmosphere, often near the poles. Saturn also has lightning, detected by the Cassini spacecraft as radio signals and occasional flashes in the clouds. Venus, with its thick atmosphere and volcanic activity, experiences lightning as well, though the details are harder to observe through the dense cloud cover. These storms are reminders that weather, in various forms, exists throughout the solar system. Even on worlds without life, the sky can crackle with energy. Our solar system is about 4.6 billion years old. The sun, the planets, and everything in the solar system formed from a vast cloud of gas and dust about 4.6 billion years ago. This cloud, perhaps triggered by a nearby supernova, began to collapse under its own gravity. Most of the material fell into the center, forming the sundae. The rest flattened into a spinning disk, where planets, moons, and asteroids gradually coalesced. The entire process took tens of millions of years. The oldest objects we've found, certain meteorites, date back to this early period. They're older than Earth, older than the Moon, remnants of the solar system's birth. In cosmic terms, the solar system is middle-aged, with billions of years still ahead before the sun exhausts its fuel and begins to die. The speed of light creates a cosmic time machine. When we look up at the night sky, we're not seeing the universe as it is right now. We're seeing the past. Light from the nearest star after the sun, Proxima Centauri, takes over 4 years to reach us. When you see that star, you're seeing light that left when you were 4 years younger. The farther away an object is, the older its light. Some stars we see died long ago, but their light is still traveling toward us. In this way, the universe preserves its history in light, sending messages across time. Every photon that reaches your eye is a messenger from the past, carrying a story of where it's been and what it's seen. The Earth's magnetic field protects us from solar storms. Our planet has an invisible shield, a magnetic field generated by the churning liquid iron in Earth's outer core. This field extends far into space, creating a protective bubble called the magnetosphere. When charged particles from the sun, carried by the solar wind, reach Earth, most are deflected by this magnetic field. Without it, these particles would strip away our atmosphere and bombard the surface with harmful radiation. Mars, which lost most of its magnetic field billions of years ago, shows us what can happen. Its atmosphere was gradually stripped away by the solar wind, leaving a thin, cold remnant. Earth's magnetic field is why we still have air to breathe, water in our oceans, and life on our world. The moon's far side is often called the dark side. That's not quite right. The moon is tidally locked with Earth, meaning it always shows us the same face. We never see the far side from Earth, but that doesn't mean it's dark. As the moon orbits Earth, sunlight illuminates all sides equally over the course of a month. When we see a new moon, the far side is actually fully lit by the sunday. The term dark side persists, perhaps because it feels mysterious, unknown, and for a long time, it was. Humans didn't see the far side until 1959, when a Soviet spacecraft photographed it. The images revealed a surface heavily cratered and lacking the large, dark area that marked the near side. The far side is different, strange, but not dark, just hidden from our view. Meteorites are fragments of asteroids that fall to Earth. Most of the material falling from space burns up in the atmosphere, creating brief streaks of light we call meteors or shooting stars. But sometimes a chunk is large enough to survive the journey and reach the ground. These are meteorites, and they're remarkably valuable to science. Meteorites are pieces of asteroids, sometimes comets, and in rare cases, fragments blasted off the Moon or Mars by impacts. They're older than any rock found on Earth, dating back to the formation of the solar system. By studying meteorites, scientists can learn about the conditions and materials present billions of years ago. Some contain organic molecules and amino acids, hinting at the chemistry that may have led to life. Meteorites are cosmic gifts, ancient stones that carry the history of the solar system in their structure. Jupiter has at least 79 known moons, probably more. Jupiter's family of moons is vast and varied. The four largest, Io, Europa, Ganymede, and Callisto, were discovered by Galileo in 1610 and are called the Galilean moons. They're large, geologically interesting worlds in their own right. But Jupiter has dozens of smaller moons as well, many of them tiny, irregularly shaped objects only a few kilometers across. These smaller moons are likely captured asteroids, pulled into Jupiter's orbit by its immense gravity. New moons are still being discovered as technology improves. Some orbit close to Jupiter, others far out in distant, eccentric paths. Each moon is a piece of the solar system's history, a story of formation, capture, or collision written in ice and rock. The Oort cloud is a vast shell of icy objects surrounding the solar system. Far beyond the Kuiper belt, at the very edge of the sun's gravitational influence, lies the Oort cloud. This region is thought to be a spherical shell of trillions of icy bodies, extending out to nearly a light year from the Sunday. The Oort cloud has never been directly observed. It's too distant, and its objects are too small and dark. We infer its existence from long-period comets, those that take thousands or millions of years to complete an orbit. These comets occasionally get nudged by passing stars or gravitational perturbations and fall inward toward the Sunday. The Oort cloud is the solar system's outermost frontier, a cold, dark reservoir of ancient ice, barely held by the sun's fading gravity. Solar eclipses are cosmic coincidences. A total solar eclipse, where the moon completely covers the sun, is one of nature's most spectacular events, but it's also an incredible coincidence. The sun is about 400 times larger than the moon, but it's also about 400 times farther away. This makes them appear almost exactly the same size in our sky. It's a temporary alignment. The moon is slowly drifting away from Earth, and in a few 100 million years, it will be too far away to fully cover the Sunday. Total solar eclipses will become impossible. For now, we live in an era when they're possible, a brief window in the history of Earth and Moon when these two objects, by pure chance, align perfectly in our sky. The Earth's atmosphere is layered like an onion. Earth's atmosphere isn't a single uniform blanket. It's divided into distinct layers, each with different properties. The lowest layer, the troposphere, is where we live and where weather happens. Above that is the stratosphere, home to the ozone layer that protects us from ultraviolet radiation. Higher still are the mesosphere, thermosphere, and finally the exosphere, where the atmosphere gradually fades into space. Each layer has its own temperature profile, chemistry, and role in protecting and supporting life. The transitions between layers are subtle but real, invisible boundaries that shape how energy, particles, and weather move through the atmosphere. We live at the bottom of this layered ocean of air, breathing the densest part, sheltered by the layers above. Voyager 1 is the farthest human-made object from Earth. Launched in 1977, Voyager 1 was sent to explore Jupiter and Saturn. After completing its mission, it continued outward, moving away from the Sunday. In 2012, it crossed into interstellar space, leaving the heliosphere and entering the region between stars. It's now more than 24 billion kilometers from Earth, traveling at about 17 kilometers per second. Despite the immense distance, it still sends back data, faint signals that take over 22 hours to reach us. Voyager 1 carries a golden record, a message from Earth containing sounds, images, and greetings in many languages. It's a time capsule, drifting through the galaxy, a quiet ambassador from a small blue planet. In tens of thousands of years, it may pass near other stars, carrying its message into the unknown. Comets are often called dirty snowballs. Comets are icy bodies from the outer solar system made of frozen water, carbon dioxide, methane, and ammonia mixed with dust and rocky material. When a comet approaches the sun, the ice begins to vaporize, releasing gas and dust that form a glowing coma and tails. The nucleus, the solid core of the comet, is usually just a few kilometers across, dark and irregular. Some comets visit the inner solar system regularly, like Halley's Comet, which returns every 76 years. Others are long-period comets, taking thousands or millions of years to complete an orbit. Comets are ancient, pristine objects, largely unchanged since the solar system formed. They're remnants from the outer reaches, visitors from the cold and dark. The sun's light takes thousands of years to escape from its core. Energy is generated in the sun's core through nuclear fusion. But that energy doesn't immediately escape. The sun is so dense that light can only travel a tiny distance before being absorbed and re-emitted by an atom. This process happens over and over, with photons zigzagging randomly through the sun's interior. It can take tens of thousands to even hundreds of thousands of years for a photon to work its way from the core to the surface. Once it reaches the surface, however, it escapes into space and takes just over 8 minutes to reach Earth. The light warming your face right now began its journey in the heart of the sun before humans existed, wandering through a maze of atoms before finally breaking free. Space is not a perfect vacuum. Even in the emptiest regions of space, there are still a few atoms per cubic meter, mostly hydrogen and helium. In some areas, like inside galaxies, the density is higher. In others, like the voids between galaxy clusters, it's lower. Space also contains magnetic fields, cosmic rays, and faint background radiation. This thin material, spread across unimaginable distances, is enough to influence the motion of galaxies, the formation of stars, and the propagation of light. Space isn't truly empty. It's more like a very, very thin gas with structure, temperature, and motion. Even in the quietest regions, there's something there, faint but real, drifting silently through the dark. Earth's rotation is gradually slowing down. Every century, the length of a day on Earth increases by about 1.7 milliseconds. The cause is tidal friction, the same process that pushes the moon farther away. As the moon's gravity pulls on Earth's oceans, creating tides, the water sloshes against the ocean floor and coastlines. This friction gradually slows Earth's rotation. Billions of years ago, days were much shorter. When life first appeared, a day might have been only 18 or 20 hours long. In the distant future, Earth's rotation will slow even more, until one side always faces the moon, just as the moon now always faces Earth. The process is gentle and imperceptible, but it's real. Time itself, measured by our planet's spin, is slowly changing. Neutron stars are the densest objects in the universe besides black holes. When a massive star explodes as a supernova, its core can collapse into a neutron star, an object about 20 kilometers across but containing more mass than the Sunday. The material inside is so dense that protons and electrons merge into neutrons, forming a kind of giant atomic nucleus. A sugar cube-sized amount of neutron star material would weigh about 1 billion tons. Neutron stars spin rapidly, often hundreds of times per second, and have magnetic fields trillions of times stronger than Earth's. Some emit beams of radiation that sweep across space like lighthouse beams, which we detect as pulsars. Neutron stars are extreme in every way: dense, fast, magnetic, and strange. The Sun loses about 1 million tons of material every second through the solar wind. The Sun doesn't just shine, it also exhales, sending out a constant stream of charged particles called the solar wind. This wind flows outward in all directions, carrying away about 1 million tons of material every second. That sounds like a lot, but compared to the Sun's total mass, it's negligible. The solar wind travels at hundreds of kilometers per second, and when it reaches Earth, it interacts with our magnetic field, sometimes causing auroras and occasionally disrupting satellites and power grids. The solar wind extends far beyond the planets, creating the heliosphere, a protective bubble that shields the solar system from interstellar radiation. The Sun breathes out into space, and we live inside its breath. There are volcanoes on Venus that may still be active. Venus has more volcanoes than any other planet in the solar system, with over 1,600 major volcanic features identified. Most are thought to be extinct, but recent observations suggest some may still be active. The surface of Venus is constantly being reshaped by volcanic activity, lava flows, and tectonic processes. The planet's thick atmosphere makes it difficult to observe the surface directly, but radar mapping from orbiting spacecraft has revealed a world dominated by volcanic plains and massive shield volcanoes. If Venus does have active volcanoes, it would be one of only 4 bodies in the solar system with confirmed volcanic activity, joining Earth, Io, and Enceladus. Venus, hot and hostile, may still be alive with fire beneath its clouds. Saturn is the least dense planet in the solar system. If you could find a bathtub big enough, Saturn would float in it. Its average density is less than that of water, about 0.687 grams per cubic centimeter. This low density comes from Saturn's composition. It's made mostly of hydrogen and helium, the lightest elements in the universe, with a small, rocky core surrounded by thick layers of gas. Despite its low density, Saturn is the second largest planet in the solar system, with a volume that could hold over 760 Earths. Its famous rings, made of ice and rock, are incredibly thin and delicate compared to the planet's bulk. Saturn is a giant balloon of gas, light enough to float, beautiful enough to inspire wonder. The Sun will eventually become a planetary nebula. In about 5 billion years, the Sun will exhaust the hydrogen in its core and begin fusing helium. Its outer layers will expand, turning it into a red giant. Eventually, those outer layers will be gently expelled into space, forming a glowing shell of gas called a planetary nebula. Despite the name, planetary nebulae have nothing to do with planets. Early astronomers thought they looked like planets through their telescopes, hence the name. In nebula will glow for tens of thousands of years, lit by the hot core left behind, the white dwarf. The nebula will gradually fade and disperse, enriching the interstellar medium with heavier elements. The sun's death will be slow, beautiful, and ultimately peaceful. A cosmic exhalation, returning material to the galaxy. Mars has ice caps at both poles. Like Earth, Mars has polar ice caps, but they're made of both water ice and frozen carbon dioxide, also known as dry ice. In the Martian winter, temperatures drop low enough that carbon dioxide from the atmosphere freezes onto the polar caps, making them grow. In summer, the dry ice sublimates back into the atmosphere, and the caps shrink. Beneath the seasonal layer of dry ice lies a permanent cap of water ice, several kilometers thick in places. These ice caps are some of the largest reservoirs of water on Mars. If they melted, they wouldn't create oceans like Earth's, but they hold enough water to be significant for future exploration and potential human habitation. Mars's poles are cold, bright, and filled with frozen history. The colors of planets come from their atmospheres and surfaces. Each planet has a distinct color, shaped by what it's made of and how it reflects light. Mercury is gray and cratered, resembling our moon. Venus is bright white, shrouded in thick clouds of sulfuric acid. Earth is blue and white, with oceans and clouds. Mars is rusty red, from iron oxide in its soil. Jupiter displays bands of white, orange, and brown, colored by ammonia and other compounds. Saturn is pale yellow, softer in hue. Uranus and Neptune are blue-green and deep blue, their colors created by methane in their atmospheres absorbing red light. Each color tells a story about the planet's composition, atmosphere, and history. The solar system is a palette, painted by chemistry and light. There are diamonds in the heart of Uranus and Neptune. Deep inside Uranus and Neptune, beneath their thick atmospheres of hydrogen, helium, and methane, the pressure and temperature become extreme. Scientists believe that under these conditions, carbon in the form of methane can be compressed and broken apart, forming diamonds. These diamonds rain downward through the planet's interior, sinking toward the core. It's not a small amount either. Models suggest there could be millions of tons of diamonds within these ice giants. Of course, they're far beyond our reach, buried under thousands of kilometers of crushing atmosphere and liquid mantle. But they're there, glittering in the dark, unreachable treasures in the hearts of distant worlds. The great dark spot on Neptune disappeared and was replaced when Voyager 2 flew past Neptune in 1989. It observed a massive storm called the Great Dark Spot, similar to Jupiter's Great Red Spot. This storm was about the size of Earth, with winds reaching 2,400 kilometers per hour. But when the Hubble Space Telescope observed Neptune a few years later, the Great Dark Spot had vanished. In its place, a new dark spot had appeared in a different location. Neptune's storms seemed to be more transient than Jupiter's, forming and dissipating over years or decades rather than centuries. Neptune is a dynamic, stormy world, constantly churning under a deep blue sky. Pluto's atmosphere expands and contracts with its orbit. Pluto has an extremely elliptical orbit, bringing it as close as 30 astronomical units from the Sun and as far as 49 AU. When Pluto is closer to the Sun, its surface warms slightly, causing some of its frozen nitrogen and methane to sublimate into a thin atmosphere. When it moves farther away, the atmosphere freezes and falls back to the surface as snow. This cycle takes 248 years, the length of Pluto's orbit. Right now, Pluto is moving away from the Sun, and its atmosphere is slowly collapsing, Observations from Earth show that the atmosphere is still present but thinning. In a few decades, Pluto will be too cold to support an atmosphere, and it will freeze solid once more, a small, distant world waiting for the sun to warm it again. The moon has quakes, called moonquakes. The moon is geologically quiet compared to Earth, but it's not completely inactive. Seismometers left on the moon by Apollo astronauts detected moonquakes, tremors caused by several different sources. Some are caused by meteorite impacts. Others, called thermal moonquakes, are caused by the sudden expansion of the surface as it transitions from the cold lunar night to the heat of day. Deep moonquakes occur far below the surface, likely caused by tidal forces from Earth's gravity. These quakes are small and infrequent, but they reveal that the moon still has some internal activity. Even a world as cold and quiet as the moon is not entirely still. The universe is filled with background radiation from the Big Bang. Everywhere you look in the sky, in every direction, there's a faint glow. It's called the cosmic microwave background, and it's the afterglow of the Big Bang. About 380,000 years after the universe began, it cooled enough for atoms to form, and light was finally able to travel freely. That light has been traveling ever since, stretched by the expansion of space into long wavelength microwaves. This radiation is incredibly uniform, with tiny temperature variations of only a few millionths of a degree. These variations are the seeds of all structure in the universe. The slight density differences that eventually grew into galaxies, stars, and planets. The cosmic microwave background is the oldest light we can see, a quiet hum from the birth of everything. Asteroids have hit Earth throughout its history. Earth's surface is marked by impact craters, though many have been eroded or covered over time. Some impacts were small, creating modest craters. Others were catastrophic. About 65 million years ago, an asteroid roughly 10 kilometers wide struck the Yucatan Peninsula in Mexico. The impact released energy equivalent to billions of atomic bombs, triggering massive fires, tsunamis, and a cloud of dust that blocked out the sun for years. This event is believed to have caused the extinction of the dinosaurs and about 75% of all species on Earth. The crater, called Chicxulub, is still visible as a ring structure buried beneath the surface. Impacts like this are rare, but they remind us that Earth exists in a dynamic, sometimes violent solar system. The sky is not always peaceful. The surface of the sun is always changing. The sun appears constant and steady, a dependable source of light and heat, but its surface is actually in constant motion. Sunspots, dark patches caused by magnetic activity, appear and disappear in cycles that last about 11 years. Solar flares, sudden bursts of energy, can erupt from active regions, releasing as much energy as a billion hydrogen bombs. Prominences, loops of glowing gas, arch above the surface, suspended by magnetic fields. And every so often, the sun ejects a huge cloud of plasma in an event called a coronal mass ejection. These eruptions send charged particles racing through the solar system, sometimes reaching Earth and triggering auroras or disrupting communications. The sun is alive with activity, a roiling ball of plasma held together by gravity and magnetism, constantly shifting, always burning. You can see 5 planets with the naked eye. On a clear night, away from city lights, you can see 5 planets without a telescope: Mercury, Venus, Mars, Jupiter, and Saturn. They don't twinkle like stars. Instead, they shine with a steady light, moving slowly against the background stars over days and weeks. Ancient cultures noticed these wandering lights and named them after gods and mythical figures. Venus, the brightest, is often visible near sunrise or sunset, sometimes called the morning or evening star. Jupiter is second brightest, a brilliant white dot. Mars has a distinctive reddish hue. Saturn is fainter but still visible, a pale yellow point. Mercury is the hardest to see, staying close to the sun and appearing only briefly after sunset or before dawn. But they're all there, planets of our solar system, visible without any equipment, silently moving through the night sky. The speed of the solar wind varies. The solar wind, the stream of charged particles flowing from the sun, doesn't move at a constant speed. It has fast and slow components. The slow solar wind travels at about 400 kilometers per second, while the fast solar wind can reach speeds of 800 kilometers per second or more. These variations create complex structures in the heliosphere, with fast streams catching up to slow ones and creating shock waves and turbulence. When the solar wind reaches Earth, it interacts with the magnetosphere, and during periods of intense solar activity, it can cause geomagnetic storms. These storms can produce beautiful auroras, but can also interfere with power grids, satellites, and communication systems. The solar wind is not a gentle breeze, but a dynamic, variable flow of energy. Galaxies come in different shapes. Galaxies, vast collections of stars, gas, and dark matter, come in several basic shapes. Spiral galaxies, like the Milky Way, have graceful arms winding outward from a central bulge. Elliptical galaxies are smooth, rounded, and lack the distinct structure of spirals. Irregular galaxies have no clear shape, often distorted by gravitational interactions or collisions. Some galaxies are classified as lenticular, shaped like a lens, with a central bulge and a disk but no spiral arms. The shape of a galaxy tells us about its history, how it formed, whether it has collided with others, and whether it is still actively forming stars. Galaxies are not static. They evolve, merge, and transform over billions of years, shaping the large-scale structure of the universe. The Andromeda Galaxy is approaching us. The Andromeda Galaxy, our nearest large galactic neighbor, is about 2.5 million light-years away. But unlike most distant galaxies, which are receding from us due to the expansion of the universe, Andromeda is moving toward us. It's approaching at about 110 kilometers per second, or about 400,000 kilometers per hour. In about 4 billion years, Andromeda and the Milky Way will collide, or rather, begin to merge. The collision will be a slow, graceful process, taking hundreds of millions of years. Stars will mostly pass by each other without direct collisions because the distances between stars are so vast. But the gravitational interactions will reshape both galaxies, eventually forming a single, larger elliptical galaxy. By that time, the Sun will be nearing the end of its life, and Earth's fate will be uncertain. But the merger itself will be spectacular, a cosmic dance played out over eons. The Hubble Space Telescope has taken over 1 million observations. Since its launch in 1990, the Hubble Space Telescope has been one of humanity's most important tools for exploring the universe. It orbits Earth above the distorting effects of the atmosphere, providing incredibly clear images of distant galaxies, nebulae, planets, and stars. Hubble has observed objects billions of light years away, captured the birth and death of stars, and helped determine the age and expansion rate of the universe. Some of its most famous images, like the pillars of creation in the Eagle Nebula of the Hubble Deep Field, have become iconic, revealing the beauty and complexity of the cosmos. Hubble has made over 1 million observations and will continue operating for years. And I in the sky looking back through time and space. Black holes are regions where gravity is so strong that nothing can escape. A black hole forms when a massive star collapses at the end of its life, compressing matter into an incredibly small, dense point called a singularity. The gravity near this singularity is so intense that it warps space-time, creating a boundary called the event horizon. Once something crosses the event horizon, it cannot escape, not even light. That's why black holes are invisible. We can only detect them by observing their effects on nearby matter, such as gas spiraling into the black hole and heating up, emitting X-rays before it disappears. Black holes can have masses ranging from a few times the sun's mass to billions of times more. At the center of most galaxies, including the Milky Way, there is a supermassive black hole, a gravitational anchor holding the galaxy together. The speed of Earth through space is faster than you think. We tend to think of Earth as a fixed point, a stable platform moving through space in a simple orbit around the sun, but the reality is far more complex. Earth orbits the sun at about 30 kilometers per second, or roughly 108,000 kilometers per hour. The sun, in turn, orbits the center of the Milky Way at about 828,000 kilometers per hour. The Milky Way itself is moving through space, falling toward the Virgo cluster at about 600 kilometers per second. And on an even larger scale, our local group of galaxies is moving toward a region of space called the Great Attractor. When you add up all these motions, Earth is hurtling through the universe at over 1,000,000 kilometers per hour. We don't feel it because everything around us is moving together, a smooth, silent journey through the cosmos. Space telescopes avoid the blurring effects of Earth's atmosphere. When astronomers look at the sky from Earth, they have to deal with the atmosphere. Air currents, moisture, and particles in the atmosphere distort and blur the light from distant objects, a phenomenon called atmospheric seeing. This is why stars appear to twinkle, and why ground-based telescopes, no matter how large, have limits to their resolution. Space telescopes, orbiting above the atmosphere, don't have this problem. They can observe the universe with exceptional clarity. Telescopes like Hubble, Spitzer, and the James Webb Space Telescope have revolutionized our understanding of the cosmos by providing sharp, detailed images free from atmospheric interference. They allow us to see farther, clearer, and deeper into space and time than ever before. Cometary orbits can be influenced by planets. When a comet approaches the inner solar system, it can have a close encounter with a planet, typically Jupiter. These encounters can dramatically alter the comet's orbit. Some comets are captured into shorter orbits, becoming periodic comets that return regularly. Others are flung out of the solar system entirely, never to return. A few are sent on collision courses with the sun or planets. In 1994, astronomers watched as comet Shoemaker-Levy 9, broken into fragments by Jupiter's gravity, crashed into the giant planet, creating massive fireballs visible from Earth. These interactions show how dynamic and interconnected the solar system is. Orbits are not fixed. They're constantly being shaped and reshaped by the gravitational dance of planets, moons, and smaller bodies. The sun's magnetic field flips every 11 years. The sun has a magnetic field, and it's far from stable. About every 11 years, the sun's magnetic field reverses, with the north and south magnetic poles swapping places. This flip is part of the solar cycle, a pattern of activity that includes changes in the number of sunspots, solar flares, and coronal mass ejections. At solar maximum, when the sun is most active, sunspots are numerous and solar storms are frequent. At solar minimum, the sun is quieter, with fewer sunspots and less activity. This cycle affects space weather throughout the solar system, influencing influencing everything from auroras on Earth to conditions for spacecraft. The sun is not a steady, unchanging star, but a dynamic, cycling source of energy and magnetism. Light years measure distance, not time. A light year is the distance light travels in 1 year, about 9.46 trillion kilometers. It's a unit of distance, not time, though the name can be confusing. When we say a star is 10 light years away, we mean it's 94.6 trillion kilometers away. Using light years makes sense for astronomy because the universe is so vast that kilometers or miles become impractical. Proxima Centauri, the nearest star to the Sun, is about 4.24 light years away. The center of the Milky Way is about 26,000 light years away. The Andromeda Galaxy is 2.5 million light years away. These distances are so large that even traveling at the speed of light, it would take years, millennia, or millions of years to reach them. Light years help us grasp the scale of the universe, even if the numbers remain almost unimaginable. Tidal forces from the moon create 2 high tides per day. The moon's gravity pulls on Earth, creating a bulge of water on the side facing the moon. But there's also a bulge on the opposite side. This happens because the moon's gravity pulls more strongly on the side of Earth closest to it and less strongly on the far side. The result is 2 high tides per day as Earth rotates beneath these bulges. The sun also contributes to tides, though its effect is weaker. When the sun, moon, and Earth align during full and new moons, their combined gravitational pull creates especially high spring tides. When they're at right angles during quarter moons, the tides are weaker, called neap tides. Tides are a visible reminder of the gravitational connections between celestial bodies. The moon's gentle tug pulling at the oceans twice a day, every day. The Drake equation estimates the number of communicative civilizations. In 1961, astronomer Frank Drake proposed an equation to estimate how many intelligent communicative civilizations might exist in the Milky Way. The Drake equation considers factors like the rate of star formation, the fraction of stars with planets, the number of habitable planets per star system, and the likelihood of life developing and becoming intelligent. The equation doesn't give a definitive answer because many of the values are uncertain. Depending on the assumptions, the number of civilizations could be just one, us, or it could be thousands or millions. The equation is less about finding a precise number and more about framing the question, are we alone? And what factors determine whether life, and especially intelligent life, arises in the universe? Europa's surface is constantly renewed by geological activity. Jupiter's moon Europa has one of the smoothest surfaces in the solar system, with very few impact craters. This suggests that the surface is young, geologically speaking, constantly being renewed by processes beneath the ice. Cracks, ridges, and chaotic terrain indicate that the ice shell is active, shifting and refreezing over time. Beneath this ice lies a liquid ocean, kept warm by tidal heating from Jupiter's gravity. The interaction between the ocean and the ice above creates a dynamic environment. Some models suggest the material from the ocean may even reach the surface through cracks, bringing with it any chemistry or even life that might exist below. Europa is not a static, frozen world. It's alive with motion. A hidden ocean churning quietly beneath a shell of ice. Neutron stars can spin incredibly fast. When a massive star collapses into a neutron star, it retains its angular momentum, but because it's now much smaller, it spins much faster, like a figure skater pulling in their arms. So neutron stars, called pulsars, spin hundreds of times per second. The fastest known pulsar rotates 716 times per second. completing a full rotation in just 4 milliseconds. At this speed, a point on the pulsar's equator is moving at a significant fraction of the speed of light. These rapid rotations, combined with strong magnetic fields, create beams of radiation that sweep across space. When these beams point toward Earth, we detect regular pulses, like a cosmic lighthouse. Neutron stars are among the most extreme objects in the universe, dense, fast, and powerful. Space is expanding, but galaxies themselves are not. The universe is expanding, with space itself stretching and carrying galaxies apart. But this expansion only affects large scales, the distances between galaxy clusters. On smaller scales, such as within galaxies or even within galaxy groups, gravity holds things together. The Milky Way is not expanding. The solar system is not expanding. Earth and the moon are not drifting apart because of cosmic expansion. Gravity is strong enough to bind these structures, but on scales of hundreds of millions of light years, where gravity's influence is weaker, expansion dominates. This is why distant galaxies are moving away from us, and the farther they are, the faster they recede. Expansion is a property of space itself, not of the objects within it, and it only becomes significant across the vastness of intergalactic distances. Stars form in clouds of gas and dust called nebulae. In the cold reaches of space, vast clouds of hydrogen gas and dust drift through galaxies. These clouds, called nebulae, can be hundreds of light years across. When a region of a nebula becomes dense enough, gravity begins to pull it together. As the cloud collapses, it heats up, eventually becoming hot enough at the center to ignite nuclear fusion. A star is born. Often, many stars form together in clusters, emerging from the same cloud. The remaining material may form planets, asteroids, and comets. The process takes millions of years, but it's happening constantly throughout the universe. Every star, including our sun, was born this way, from the collapse of a cloud in the quiet darkness of space. The North Star hasn't always been the North Star. Polaris, the North Star, currently sits nearly aligned with Earth's axis of rotation, making it appear almost stationary in the sky, while other stars circle around it. But Earth's axis wobbles slowly over time, a motion called precession, taking about 26,000 years to complete a full cycle. Because of this wobble, the position of the celestial poles shifts. The different stars take turns being the North Star. About 5,000 years ago, the star Thuban in the constellation Draco was the North Star. In about 12,000 years, the bright star Vega will hold that position. Polaris won't always guide travelers. The sky changes, slowly and patiently, as Earth wobbles through the ages. The sun's gravity keeps comets in orbit for millions of years. Comets from the Oort cloud can have orbits that take millions of years to complete. They spend most of their time far from the sun, cold and inactive, moving slowly through the outer reaches of the solar system. But the sun's gravity, though weak at those distances, is still strong enough to hold them in orbit. Occasionally, a passing star, gravitational perturbation, nudges the comet inward, sending it on a long journey toward the inner solar system. As it approaches the sun, it warms, develops a tail, and becomes visible from Earth. Then it swings around the sun and heads back out, beginning another slow circuit that may last millions of years. These long-period comets are travelers from the edge, visitors that remind us of the vast, unseen boundaries of the solar system. Auroras occur on other planets with magnetic fields. Earth's auroras, the northern and southern lights, are caused by charged particles from the sun colliding with molecules in our atmosphere, guided by Earth's magnetic field toward the poles. But Earth is not alone. Any planet with a magnetic field and an atmosphere can have auroras. Jupiter's auroras are the most powerful in the solar system, glowing brightly in ultraviolet light and driven partly by particles from its volcanic moon, Io. Saturn also has beautiful auroras, often appearing as shimmering rings around its poles. Even Uranus and Neptune, distant and cold, have faint auroras detected by spacecraft. Mars, with its weak and patchy magnetic field, has localized auroral glows in regions where the crust retains ancient magnetism. Auroras are a universal phenomenon, a light show created by the interaction of particles and magnetism, playing out across the solar system. Galaxies can be billions of light years apart. The universe is vast beyond comprehension, and galaxies are spread across it like islands in an ocean. The nearest large galaxy to the Milky Way, Andromeda, is about 2.5 million light-years away. Most galaxies are much farther. The observable universe extends about 46 billion light-years in every direction, and within that volume, there are an estimated 2 trillion galaxies. Some of these galaxies are so far away that their light has been traveling toward us for over 13 billion years, showing us what they looked like when the universe was young. These distant galaxies are separated by unimaginable voids, vast empty regions where almost nothing exists. The scale is difficult to hold in the mind, but it's real. The universe is a place of profound distances, where light itself takes billions of years to cross from one galaxy to another. The sun will shine for about 10 billion years total. The sun is currently about 4.6 billion years old, roughly halfway through its life. It will continue burning hydrogen in its core for another 5 billion years, shining steadily as it has for eons. After that, it will enter its red giant phase, swelling up and consuming the inner planets. This phase will last for about 1 billion years, during which the sun will fuse heavier elements and shed its outer layers. Eventually, it will eject those layers into space, forming a planetary nebula, and the core will collapse into a white dwarf. This white dwarf will slowly cool over trillions of years, eventually fading into darkness. The sun's life is long by human standards, but in cosmic terms, it's a finite, predictable story. One star among billions, burning, evolving, and eventually fading. Some moons are tidally locked to their planets. The moon always shows the same face to Earth because it's tidally locked. This means its rotation period matches its orbital period, so one side always faces us. This isn't unique to the moon. Many moons in the solar system are tidally locked to their planets. It happens over time due to tidal forces. The planet's gravity creates bulges in the moon. The friction from these bulges gradually slows the moon's rotation until it becomes synchronized. Once locked, the moon stays that way, rotating once per orbit. From the surface of a tidally locked moon, the planet would appear to hang in the sky, always in the same position, while the stars slowly wheel overhead. It's a different kind of sky, a different kind of day and night. Earth's atmosphere protects us from meteors. Every day, thousands of small rocks and particles from space enter Earth's atmosphere. Most are tiny, no larger than grains of sand. As they plunge through the atmosphere at high speed, friction heats them to incandescence, creating the streaks of light we call meteors, or shooting stars. Most burn up completely before reaching the ground. This constant bombardment would be dangerous on a world without an atmosphere, like the moon, where every meteorite strikes the surface. But Earth's thick atmosphere acts as a shield, burning up most incoming debris and protecting the surface. Only the largest objects make it through, and those are rare. The atmosphere, often taken for granted, is one of Earth's most important defenses, a blanket of gas that keeps us safe from the hazards of space. The cosmic web is the largest structure in the universe. On the largest scales, the universe is organized into an immense structure called the cosmic web. Galaxies are not distributed randomly. Instead, they cluster along vast filaments of dark matter, stretching across hundreds of millions of light years. Where these filaments intersect, enormous galaxy clusters form. Between the filaments lie voids, regions almost devoid of galaxies. The cosmic web resembles a sponge or a network of threads, a delicate, intricate pattern that spans the observable universe. This structure formed over billions of years, shaped by gravity and the initial density fluctuations from the Big Bang. The cosmic web is the architecture of the universe, the largest pattern we know, connecting galaxies across unimaginable distances. Thank you for spending this time with me, drifting through the solar system and beyond. We've traveled from the surface of distant moons to the heart of storms on Jupiter, touched the icy edges of the Kuiper Belt and felt the heat of the sun's core. We've watched light travel across billions of years, felt the pull of gravity shaping galaxies, and listened to the quiet rhythms of planets and their orbits. And through it all, we've been here, breathing slowly, resting gently. The universe is full of wonder, but it's also full of peace. In the vast stretches of space, in the quiet orbits of moons and planets, there's a stillness that we rarely find in daily life. And maybe, in learning about these distant places, you've found a little of that stillness too. The cosmos is ancient and vast, but it's also patient and gentle, unfolding at its own pace, indifferent to hurry. There's comfort in that, in knowing that somewhere out there, moons orbit in silence, stars burn steadily, and galaxies drift through the dark. The universe doesn't rush, it simply exists, moment by moment, eon by eon. And tonight, you've been part of that existence, connected to it through thought and wonder. If you're still awake, let your thoughts continue to drift like dust motes in a sunbeam, light and free. If you've already slipped into sleep, may your dreams be as vast and peaceful as the cosmos itself. May you rest among the stars, cradled by the quiet infinity of space. Thank you for joining me on Sleep Plus Knowledge. If this helped you rest, consider subscribing so others can find their way here too. There's always more to explore, more wonders to discover, more peaceful facts to drift through. The universe is patient, and so are we. For now, rest well. The stars will still be there tomorrow, shining quietly, waiting for you to look up again. Good night, and may your sleep be as deep and peaceful as the space between the stars.